second assignment,
Hmm. You
and
submitted when?
yeah, submitted.
Which one? Wait, let me show the screen. You're drawn the graphs. Can you show me now?
Sir, I have not submitted the third assignment. I have submitted the transfer functions and the
No, no. I am talking about.
multiple inputs and
No, no, no. I am talking about this. So
no,
this is
sir.
what. See, this is what I am expecting. This.
Okay.
Hmm. Ah, see now here, you can see the screen, right? Vaidehi?
Yes, sir.
Yes, yes, sir.
Here, you can see the screen. See? Oh, what I can. See now, this is your step input, okay, and this is what is your output, okay. This is your ramp input, and this is your output. Now this at any time t, this is going to give me the error. So at which point there is no error, that is input is equal to output, that is at this point. At this point, here onwards, input, see this is my output, this is my input. The output is more, here the output is less. Now in case of sinusoidal, so this is my input and this is my output, and at any point you can get the error. So the control, as a control engineer, you have to see that this and this, they maps, on each other. I said they fit exactly on each other. Is it clear what I said? That means the error is zero, and this is what I wanted you to understand from this assignment. Is it clear what I said? Hello?
Yes,
Yes, sir.
sir.
Yes, sir.
Yeah. Both should match. That means the error is zero, I say. And this is a technique. This graph you can get in MATLAB. In MATLAB you can get this graph. And remember, when you are solving this, you try this either MATLAB, using MATLAB or on graph paper. You have to take the values in radian. Change your calculator to radian mode. This is what I have mentioned. You have to change the calculator to radian mode. Otherwise, you will not get the graph properly. Hmm? Okay. Okay. Of course, it has this classical method has its own importance. Now coming to Laplace transform. So I told that there is a classical solution method, Laplace transform method, and analog computer method. So you know the definition of Laplace. That is, if you want to find out the Laplace of f of t, this cursor is visible, isn't it? This cursor, Laplace of f of t, uh, is equal to, let's say, fs. So how do you obtain Laplace of f of t? By definition, it is 0 to infinity f of t into e raised to minus st dt. Okay. This is the definition, right? So now if my say theta is h, that is my input disturbance is h, step input. So Laplace of h is equal to 0 to infinity. Okay. What is my function? It is h into e raised to minus st dt. Okay. Now h is a constant step input. Okay, so that will come out of the integration sign. So h 0 to infinity e raised to minus st dt. So integration of e raised to minus st will be e raised to minus st upon minus s with respect to t and 0 to infinity. Right? Hello. Are you understanding what I'm saying?
Yes, yes.
E raised to integration of e raised to minus st will be e raised to minus st upon minus s. Now you substitute this in these two values, upper limit and lower limit. Here there is a mistake, this minus s. So minus s now I am taking out. Okay, so h upon minus s is into bracket. Now substitute the value of t as infinity, upper limit. So e raised to minus infinity or 1 upon e raised to infinity. Okay, so that is 0. Now if you substitute minus 1, so this will be e raised to, if you substitute 0 now, if you substitute infinity, if you substitute you are getting 0, and if you substitute 0 t ka value, so e raised to 0 that is 1. So 0 minus 1, so that is h upon s. You understood this? Why
Yes,
did
yes, sir.
h upon s? Now similarly, suppose if theta I is equal to ht, this is ramp entry. So again Laplace of ht is equal to 0 to infinity ht, this is my function, e raised to minus st. Now h is a constant, I will take it out, integration 0 to infinity. So 2t into e raised to, now this you have to solve by UE rule, product rule, isn't it? Integration of u dv, so that is uv minus integration v into dv, correct? U into, what is UV rule? You remember? Integration of UV, U into integration V minus integration of, so let us see now this, you apply this over here. So T, okay, so this is LIAT, isn't it? LIAT, that rule you have to apply. So exponential will be at the end. So this is in order. So t, look from here, you now look here, t into integration of e raised to minus st dt, that is nothing but e raised to minus st upon minus s, and limit 0 to infinity minus integration. Now you have to take derivative of first, isn't it? Integration of u is what? U integration of v minus integration of u dash into integration of v. Okay, so now derivative of t will be 1, and integration of e raised to minus st will be this, e raised to minus st upon minus s. Now again you have to take the integration of this, that is nothing but s square. So like that, if you do and if you substitute, then finally you are going to get minus h upon s square. So if I say Laplace of 3t, so Laplace of 3t, now directly you can use this rule. So this is not this is h upon s square, not minus h upon s square, plus h upon s square, because this is 0 minus 1 and this is minus. So minus minus plus. So Laplace of 3t will be 3 upon s square. Similarly, now third example, now my input disturbance is h sin omega t. So Laplace of h sin omega t, you have to again solve by this method, by definition. So you will get this h omega s square t omega square. So like that it is. Okay, so every time you don't have to use this definition, because then it will take time. So that's why you have to refer the table in which the Laplace is already given. Okay, so this is what is nothing but Laplace transform. That is what we will see now. So Laplace of 3t will be 3 upon s square. Laplace of 3 will be 3 by s. and so on. Laplace of dx. So now you have to simply replace, this is the rule, huh? S into Laplace of x, Laplace of d square x. So that will be s square into Laplace of x. This is first derivative, this is second derivative. So Laplace transform method of solving linear differential equation is applied to control system transfer function to yield response solution for specified inputs to a system. So how to do that? So these are the steps. So transfer function theta O upon theta is equal to f of d. So write in terms of Laplace. So Laplace of theta O upon Laplace of theta I is equal to f of s. Then you cross multiply. So if you cross multiply, Laplace of this is equal to, this will go here. This is the second step. Now you convert time domain to Laplace domain. So transform theta I to this. And then you get the Laplace inverse. To again come back to time domain. Okay, let us see now. When we will take examples, we will come to know. Okay, so first example, look at this. So transfer function is given by this theta O upon theta I. So one question on this will come in the examination. So theta O upon theta I is equal to k upon this AD square plus BD plus 1. So find the response in time domain form for an input disturbance in RAM form given by theta I is equal to ht. So I will now write this in Laplace form. So Laplace of theta O upon Laplace of theta I is equal to k upon as square plus bs plus 1. Now I want to find out the response. So Laplace of theta O is equal to this Laplace of theta I into k upon this. So I am taking this. Now theta I is ht. So Laplace of theta I, that is Laplace of ht, will be h upon s square. That is what we saw now. And it is also, this will be given, this in the examination, all the Laplace transform as well as inverse transform will be given. So you don't have to, work out from the definition. So now Laplace of theta O is equal to, you substitute now h upon s square. So you will get hk upon s square into a square plus bs plus 1. Now this is a quadratic equation. So this can be factorized like this. A square plus bs plus 1, I can factorize like this. 1 plus t1s and t2s. Okay. So now directly you look in the table. That is rule number 14. I will show you the table now. Here is the table. Yeah, this is the table. Laplace transform. This is your first degree. This is your second degree. This is Laplace transform. This is like Laplace inverse of h by s is h. Laplace of h is h upon s. Laplace of ht is h upon s square. So Laplace inverse of h upon s square is ht. Step input, ramp input, sine input. So Laplace of h sine omega t is h upon omega plus s square upon omega. Now here you have k upon t into e raised to minus t upon capital T. This is called as the free response of first order system. Just have a look properly, try to understand this. Free response of first order system is given by this, and Laplace of this is k upon 1 plus ts. So Laplace inverse of k upon 1 plus ts will be this, and so on. So now you look at this. I was telling you what we have. The question number 1, rule number 14. This is second order system. This is called as a zeta, zeta, that is damping ratio. Is a damping ratio. So for second order system, when the damping ratio is 1. So in second order system, there are again different type of system, that is oscillating, non-oscillating, वगैरह ऐसा है. So in second order system, zeta is more than 1. So this is my Laplace domain, and this is my time domain. Okay, so Laplace inverse of this. So this will be given. So now you can write this in time domain. Now if you look at this, you will get one as a complementary solution and another as a. So one is your transient and another is steady state. Try to understand this properly. Now this rule we will apply for this question. That is this. So this exactly conforms to your rule number 14. S square, and this can be factorized in this form 1 plus t1s and 1 plus t2s. So this is the time response for this ramp input. So now if you see carefully here, you can see particular solution and complementary solution here. That is transient and steady state response. So steady state response in this will be hk into this t minus, if you open this bracket, so hk into this, and this will be your transient response, that is e to the part wala. Exponential part wala, that will be your transient response, that is complementary. So if you look now, so ये जो part है hk into this, that is steady state response, and this is your hk into this part, that is your transient response. Yes, sir. So for this particular question, my steady state response is going to be this. Okay, now let's have a look on this. Okay, so directly you get answers very fast. Look at this now. Now here the response is given Laplace form. में. Directly they are given theta O, and find the response in time domain form. So s plus 3 upon s square plus 3s plus 2. Now you have learned something about partial fraction. So using partial fraction, you will get s plus 3 upon s square plus 3s plus 2 like this. And you can get the value of a and b. So that means now theta O, look at this, theta O s can be written as this, minus 1 upon s plus 2 plus 2 upon s plus 1. Now you write this, that is ये है, this you have written in terms of this. Now you write this in 1 plus ts form. So 1 2 कॉमन ले लो यहाँ से, so you will get 1 plus s by 2 और ये ऊपर जाएगा, and this is already in 1 plus ts form. So now both are 1 plus ts, 1 plus ts. Now here, what is the value of t? Value of t is 1. And here, what is the value of t? Half, if you compare. What is the value of k here? Minus half. And what is the value of k here? 2. So now let us convert this into time domain form. So we will take Laplace inverse of this. Laplace inverse of this. Okay. So this is k upon, you have to compare this with k upon 1 plus td. K upon 1 plus td. So k is minus half, t is half. K upon 1 plus td, k is 2 and t is 1. So what is the Laplace inverse of k upon 1 plus td? We will refer the table. Rule number 4. K upon 1 plus ts or k upon 1 plus td. That is nothing but free response of first order system. This all you will learn second order system. Zeta is equal to 1, zeta is less than 1, zeta is greater than 1. Okay, so now here it is k upon t into Laplace inverse of this is k upon t into e raised to minus t upon t. So value of k is minus half and t is half. So we'll just substitute that and write it. Time domain. Minus half, t is half, e raised to minus 2t. No? Minus it is t into t, capital T. So look at this. It is k upon t into e raised to minus t upon t. So value of t is half. So minus t upon half, that will be nothing but e raised to minus 2t. And similarly, for this also you can write Laplace inverse. So that means, see, देखो, now here for this particular transfer function, the response is in exponential form only. That means what inference you can do, that it will remain in steady state. It will never remain. It will never approach steady state. It will remain only in transient response only. There is no steady state output like this. यहाँ पे कैसा steady state output था, hk into t minus t1 minus t2. But like this, there is no integer value or there is no fixed figure here. It is all exponential. That means it will remain only in transient state. This is what final response is, this minus e raised to minus 2t plus 2 into e raised to minus t. So we'll go for next example now. Response in Laplace is given by this 2 into s plus 6 upon s into s plus 2 s plus 4. Find the response in time domain, that is theta or t. Okay, so now we are writing this partial fraction कर लो इसका a upon s, b upon s plus 2, c upon s plus 4. You get the values of this a, b, c, a, b, c. That is, this is just algebra. Okay, इधर मल्टीप्लाई उधर मल्टीप्लाई कंपेयर करो. Okay, s square coefficient, s coefficient, I did not tell you. So now this can be written as a का value is 1.5. So 1.5 upon s. B का value is minus 2. Minus b is equal to 2. So b is equal to minus 2. So this is written as minus 2 upon s plus 2. C is half, 0.5. That is 0.5 upon s plus 4. Now you write down in k upon 1 plus ts का फॉर्म में फर्स्ट ऑर्डर. तो k upon 1, this is तो h upon s का फॉर्म में. So Laplace inverse of h upon s is h. So you will get this as 1.5. See that time domain में. Now यहाँ पे 1 plus ts के फॉर्म में if you want to write, it will be 1 plus s by 2. One plus s by 2. 2 you are taking common. So 1 plus s by 2 and 2 will get cancelled. And here again 1 plus s by 4. So here value of t is 1 by 4, value of k is half. Here value of t is half, value of k is, and then you can apply that formula, that is Laplace inverse of, that is rule number 4. Laplace inverse of k upon 1 plus ts is nothing but this k upon t e raised to minus t upon t. And you will get this answer. Now again, what will be the, this is what is your steady state response 1.5, and this is my transient response. So after some time I am going to get a, this system, this particular system which is represented by this, is going to achieve a steady state response of this value of 1.5. Next question now. What is this? And in this question here it was given also. F of Laplace values are given. Hmm. Here also it is given time domain, that is Laplace of A is A by S, AT is A by S square, and this e raised to minus AT is 1 upon A plus S. So this is given. So you have to find out the response of the system and whether system will achieve steady state or transient. So again now this is phi upon S, S plus 1, S plus 2. Now directly this you can write 1 plus Ts का form में. So this is 1 plus half S. This is already there. 1 plus Ts. Of course before that you have to convert it into, you have to use partial fraction S, S plus 1, S plus 2. And similarly you have this also, pi by 2 S square. So if it is like this, then you can use this rule number 14, and over here you can use rule number 11. Then next, theta O is 10 upon S plus 4, S plus 2. So again this is written like this, A upon S plus 4, B upon S plus 2, using partial fraction, and using table you convert it into time domain form. Now this you have to solve, okay, with the, I already solved this, and you have to submit this. So system has transfer function in time domain form. It is required to study the nature of the system by examining its response to step input disturbance theta is equal to 2. Okay, so how to do this now? Laplace of theta O, theta I is equal to this. Phi into, first you will write it in Laplace form of S वगैरह ऐसा. Then use partial fraction. Now theta I is given as 2, remember, okay, and it is step input. So Laplace of theta I will be 2 by S. So here you have to write this as 2 by S. So that means this whole thing, ये पूरा जो है, that you will have to multiply by 2 by S. So you multiply these by 2 by S. So now here using partial fraction I got these factors, इसका ये factors मिल गया, and पूरे को मैंने 2 by S से multiply किया, I multiply by 2 by S. So 37.5 into 2, 75 upon S, 25 into 2, 50, again upon S you have, here you have S, and same 42.5 into 2, 85, and again you have S here. So everywhere you have S. Now you have to compare now S into 3S plus 1. So this is rule number 8. देखो rule number 8 देखो, this HK upon S into 1 plus TS. Similarly you have to compare this, and you have to compare this. So हर एक का you write Now here iska it is this, for this it is this, and again for this it is this. This is here I have shown how to get these values partial. This is a partial fraction का method है. Like this has been written as a upon bs plus 1. This is bs upon this because it is quadratic, and this is c upon this. And how to get the values of a, b, c. So this goes as your next assignment. Only one question. So we'll stop here. Have you understood this?
Yes, sir.
Yes, sir.
Sure, no? Okay. थोड़ा practice करो. Okay. Okay. Thank you. We'll stop here.